Alright, this should be a pretty quick and simple video. Here we're going to be basically talking about differentiability. Differentiability is it's not really continuity, it's actually a different concept, but we can see that they are related in a certain way. So if you remember back to an earlier video, much earlier in the series, where we looked at continuity, we knew that there were certain parameters that must be met in order for a function to be deemed continuous. So similarly, there are certain things that we need to say or that must be true in order for a function to be differentiable. So what exactly does that mean? Differentiability simply means that a function has a derivative at a certain point. If you say that a function is differentiable, you can differentiate it, that means that you can take its derivative. So, in other words, the slope of the tangent line exists there. So if we wanted to speak from a more formal perspective, we can say that formally f is, this seems to be glitching again, f is differentiable at some x equals a. It's differentiable when x is equal to a, or at this point a, if the limit as a, or rather, let's do this. If this limit here exists, if our f prime of a is equal to limit as h approaches 0 of our f of a plus h minus f of a over h. This limit here, if this limit exists, then our function f is differentiable at that point a. And this makes sense if you remember in the last video when we were looking at the definition of a derivative. The definition of a derivative is this limit here. We use this limit in order to find the derivative. So it makes sense if this limit is what we use to find the derivative. If this limit does exist, then clearly that means that the derivative exists and this function is differentiable. So hopefully that makes sense. So if this limit here exists and is a finite number, then the function is differentiable. The derivative does exist at this point a. Now, what was it that I was saying about continuity, differentiability and continuity at the beginning of this video? What I was trying to say there was that a key fact here to know is that if a function is differentiable at some point x equals a, then it is automatically continuous at x equals a. If a function is differentiable, then it must also be continuous. This does not actually always work in the opposite direction though, right? The reverse is not always true. It's possible that a function can be continuous but not differentiable, right? All functions that are differentiable are also continuous, but not all functions that are continuous are also differentiable. So it doesn't go both ways. Differentiability implies continuity, but not the other way around. So when is a function not differentiable? A function fails to be differentiable at a point in a few common cases, right? The first one having to do again here with continuity and discontinuity. A function is not differentiable. It's not differentiable, one, if a discontinuity exists. A discontinuity exists. If the function is discontinuous, then it is not differentiable. So that means if we have a jump discontinuity, a hole, or a vertical asymptote, our function is not differentiable, right? That makes sense. If we have a function going on like this, there's a jump, then there is no derivative there. If we have a function and there is a hole, there is no point there, so there is nothing to differentiate. There is no slope that we can even speak about, so it's not differentiable. This is a vertical asymptote. Secondly, if we have a corner or a cusp, so corners or cusps. So if we had a function like the absolute value function, which looks like a v, well, the function has a derivative here, 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 but this point here, for example, if this was our function, the absolute value of x, then here, when x is equal to 0, that function is not differentiable. Speaking more formally, again, it's because the derivative, the left-handed slope and the right-handed slope don't match, so it's non-differentiable. At any point like this, there is no derivative. So any of these corners, there would not be a derivative. And when I say a cusp, that is not the same thing as a corner. A cusp is something more like this. If you had something going on like that, this cusp here, there would be no derivative there. So the function is not differentiable at corners or cusps. And finally, if we're looking at something like a vertical tangent, so if we had a function looking something like this, well then all over here, this vertical component that is just a straight vertical line, well, there the slope is infinity, and so it is not, that means that there is no derivative. The tangent line is vertical, so the slope is infinity, and so that's not a real number. So that means it is not differentiable. So these are the three things to keep in mind. If a function is discontinuous, if it has a corner or a cusp, or if it's a vertical tangent, at those points, it is not differentiable. So just to keep in mind, differentiable functions must be smooth and continuous, with no sharp turns or breaks. So on the subject of left-handed limits and right-handed limits, or rather left-handed derivatives and right-handed derivatives, in order for a function to be differentiable, the left-handed derivative and the right-handed derivative must be equal. This is something that we saw with limits as well, right? So nothing that is too crazy here. So if we had our limit as h approaches 0 from the left of this a plus h minus f of a over h, this must be equal to the limit as h approaches 0 from the right of our same thing here. So only if this is true, the left-handed derivative and the right-handed derivative must agree. If they match, the derivative exists. If not, there is no derivative at that point. So hopefully this is making sense. This should just be a pretty quick video where I just wanted to talk about the different criteria here, or when a function rather is not going to be differentiable. So on the exams, you may expect to see your professors giving you different graphs with combinations of different features, maybe something like this, and there's a break there. Something like this, and they may give you this point, or this point here, or this point over here. This point to different portions of the function and asking you whether it is differentiable. They can also ask you whether it's continuous, whether it's differentiable. Just keeping these things in mind, you should be able to answer these questions pretty easily. So hopefully, well, that does bring us to the end of this video. So hopefully you found it useful. If you did, please show your support by liking and subscribing. Leave in the comments any questions you may have, and I will see you in the next video.